Hey there, physics lovers. Have you ever shouted inside a big empty hall and heard your own voice bouncing back? That's not magic, that's reflection of sound waves. But wait, it's not just sound that reflects. Every wave, light, water, or even a pulse on a rope behaves this way when it meets a boundary. Now imagine a wave pulse traveling along a stretched rope. What happens when it hits the end? Part of the energy returns, that's reflection, and part of it continues into the next medium, that's transmission. This happens because the properties of the medium change, tension, density, or elasticity, causing a mismatch in how easily the wave can move, what we call mechanical impedance. So whether it's an echo, a ripple at a pond edge, or a pulse on a string, every time a wave encounters a boundary, reflection steps in to tell the story. Now let's talk about what happens when the wave hits a fixed end, like a rope tied tightly to a wall. Here's the key. The wall can't move, so the particle at that point has zero displacement, it's stuck. That means when a crest reaches the wall, it can't rise up, instead, it reflects as a trough. The wave comes back with the same speed and amplitude, but its phase flips by 180 degrees, or we can say there's a phase reversal. If you've ever seen a rope pulse travel to a fixed wall, you'll notice the returning pulse is upside down. This inversion happens because the boundary acts like a mirror that also flips the image vertically. And when the incident and reflected waves overlap, they create regions where waves seem to stand still. Yes, that's how stationary waves are born. Now, let's loosen things up, literally. What if the wave travels to a free end, say, a string attached to a light ring that can slide up and down freely? In this case, the end particle is not fixed. It moves with maximum displacement, so when a crest arrives, it bounces back as a crest again. That means the wave is not inverted, the phase remains the same, or we say there's zero phase change. Both the incident and reflected pulses have the same speed and amplitude, and they reinforce each other naturally. You can actually try this with a rope tied to a smooth ring, send a pulse, and you'll see it return in the same orientation. It's the wave's way of saying, freedom feels good, no flipping today. Alright, time to get a bit mathematical, but don't worry, it's smooth sailing. We introduce a new quantity called mechanical impedance, represented by Z. It is defined as the ratio of the wave driving force to the particle velocity in a medium. When a wave reaches a boundary, the amount of reflection depends on how different the impedances of the two media are. Let Z1 be the impedance of the first medium and Z2 of the second. The reflection coefficient R is given by R equals Z2 minus Z1 divided by Z2 plus Z1. The transmission coefficient T is given by T equals to Z2 divided by Z2 plus Z1. Now, if Z2 is much greater than Z1, similar to a rigid wall, the reflection coefficient becomes approximately -1, which means the reflected wave is completely inverted. But if Z2 is much smaller than Z1, like a free end, the reflection coefficient becomes +1, meaning the wave reflects without inversion. So, the mismatch in impedance decides whether the reflected wave returns upright or flipped. Let's go step by step through the core derivation, the mathematics behind reflection. We start with a wave traveling in medium 1, y1 equals a1 sine of k1x minus omega t. When it meets the boundary of medium 2, two waves appear, a reflected wave and a transmitted wave. At the boundary, two important conditions must be satisfied. The displacement of particles on both sides must be the same. The forces on both sides must balance, which means T1 times slope in medium 1 equals T2 times slope in medium 2, or equivalently, Z1 multiplied by bracket A1 minus AR bracket equals Z2 multiplied by AT. Solving these boundary conditions, we obtain the ratio of reflected amplitude to incident amplitude, AR divided by A1 equals Z2 minus Z1 divided by Z2 plus Z1. The ratio of transmitted amplitude to incident amplitude, AT divided by A1 equals to Z2 divided by Z2 plus Z1. These are the reflection and transmission coefficients. Let's connect this to real-life cases. When a wave moves from a light string to a heavy string, say, from a thin cord to a thicker one, it's like going from a rarer to a denser medium. Here, reflection happens with a phase reversal, crest becomes trough. But if the wave moves the other way, from heavy to light, it reflects without inversion. And even though the reflected and transmitted amplitudes differ, total energy remains conserved, nothing is lost, only shared differently. You can see the same behavior in sound waves. When they travel from air to a wall, most of the energy reflects, which is why you hear echoes so clearly in an empty room. Time to tie it all together. Reflection of waves in a nutshell. Whenever a wave meets a boundary, part of it returns, reflection, and part continues, transmission. At a rigid boundary, the wave flips, crest to trough, phase shift of 180 degrees. At a free boundary, it reflects upright, no phase change at all. The reflection coefficient R equals Z2 minus Z1 divided by Z2 plus Z1 tells us how much of the wave returns, and the impedance ratio decides the direction and strength of reflection. From echoes in sound to reflections in water and even electromagnetic waves bouncing off satellite dishes, the same principle holds everywhere. And that's the magic of reflection, simple, predictable, and everywhere around you. I hope you now see how every boundary in nature plays its own version of mirror on the wall. See you in the next session where we'll uncover even more fascinating behavior of waves in motion.